let's take a look at how the temperature boundary condition gets incorporated into the framework that we have been discussing. And the temperature boundary condition is called an essential boundary condition, and I'll indicate why. This is in contrast to the flux, which is, as we saw, a quote-unquote natural boundary condition. So we have our 4 nodes arranged along a line, and I've shown it within the context of the bar. And this is the assumed shape for our temperature. And we have 4 algebraic equations here relating temperatures at neighboring nodes. And I've brought the equation at the first node onto the right-hand side. The reason I did that is because it involves this term, the gradient at the left boundary, and that's the heat flux at the left boundary. And that's not known. So this equation involves an unknown on the right-hand side. So I've set it aside. On the other hand, at the left boundary, we know the temperature from the temperature boundary condition. Okay, so now I bring in the additional equation from at node 1 from that temperature boundary condition. The shape that we have assumed has to essentially satisfy that, that equation. That is, this value of the nodal temperature has to be T0. It's essential for it. Which is why this is known as an essential boundary condition. Okay, that's the terminology, and contrast it to the flux boundary condition here, which you can't say that the shape has to essentially satisfy that. In fact, we'll see that the shape won't satisfy that the natural or the flux boundary condition. So the solution proceeds in 3 stages. So in the first stage, what you do, so this is the first stage, you look at all the nodes that have essential boundary conditions on them, and you just assign the corresponding temperature value. So for here, the solver would look at this node and say, hey, there's an essential boundary condition on that node, and that value of temperature has to be T0, and so you know that value. Now you come to these 3 equations. This is known, but this is unknown, this is unknown, this is unknown. So you have now these 3 nodal temperatures that are unknown, but you have 3 equations. So you have 3 equations and 3 unknowns, and so you solve them together by inverting that subset of the stiffness matrix, and that's step 2. In this case, that would involve inverting a 3x3 matrix. Now people are doing ridiculously large problems, 100 million unknowns. So you're inverting 100 million by 100 million stiffness matrix for very complicated problems. And if you do it cleverly and you have very fast computers, you can do that with today's computers. And then after stage 2, I know all my nodal temperatures. Okay, so all the nodal temperatures have been determined, and I basically know my temperature distribution. Then what do I do with this equation here? It turns out you can do something very important. So in the third stage, you can come to this equation and say, hey, now I know T1 and I know T2, and this is a known quantity, so I can determine the flux at the left boundary. And if I take Q1 and multiply it by the area, that's the amount of heat flow leaving or entering through the left boundary. And I can do I can do a check on the solution, whether the solution satisfies the heat balance or energy balance. So I can check that the heat flow coming in, that's this over here, plus the heat generated, which I know, that's Q times the volume, is equal to the heat going out, which I know from the boundary condition. So this entity turns out is very important to check the energy balance, and it's called a reaction in ANSYS. And you can ask, you can request what the reaction is from ANSYS and then do a check on the energy balance, and you'll be doing that. It's called a reaction because it comes, that terminology comes from structural mechanics, where this entity would be the force at the essential boundary. So if you're if you're fixing the displacement, or you're fixing the left boundary, then this reaction would give you the force that's required to hold that boundary there, or that's a reaction. And this three-step process is very general, and for any finite element solver is going to use this three-step process. Step 1 and step 2 are necessary, and step 3 is highly recommended to check on whether your solution satisfies fundamental physical principles such as energy conservation or equilibrium.